thanks. Okay, let's move on. Okay, by the way, just a reminder, fourth milestone is due today, and fifth milestone is due this Friday. Okay, please check, mark your calendar. Okay, fourth today and fifth this Friday. Okay, let's move on. We are talking about hazard issue, right, in the pipelining. And there are three kind of hazard: structural, data, and control hazard, right? And last time we discussed data hazard. And today, we will focus on this control hazard. And this one is also fifth milestone, the control hazard detection and resolution, okay? So control hazard, this one. Okay, this one, Konu, can you please?
Can you hear me? A branch determines the flow of instructions. Fetching the next instruction depends on the branch outcome. Pipeline can't always fetch correct instruction. Branch instruction is still working on ID stage when fetching the next instruction.
Okay, thanks. Control hazard. Control hazard is coming from branch instruction. Okay, that comes from a branch instruction, and branch instruction potentially change execution flow, right? So this is an example. So conditional branch instruction. You have to compare these two. Branch equal, right? These two are equal. Then you branch to this label, this instruction. Otherwise, you fall through, right? So depending on the condition, it changes the execution flow. If branch is not taken, you execute PC plus 4 located instruction, right? Otherwise, you branch. And this one is conditional branch instructions. And when it comes to unconditional branch instructions, like JAL, jump and link, right? Jump and link and foo. So no condition check. You always branch to that label foo, right? The label and execute it and return back, right? So unconditional, no condition check. So it is changing. That instruction is changing execution flow, right? So if you don't have JAL, then PC plus 4, located instruction, next instruction will be executed. But because of this guy, it changes execution flow, right? And if you draw pipeline execution diagram, it looks like this, right? Fetch, decoding, and execution. And branch is resolved in execution stage, right? Branch resolution. What do you mean by branch resolution? The first one, destination computation. Destination computation. Okay. What is destination? PC plus sign extended immediate. That is destination, right? Second thing, taken, not taken decision. Taken, not taken decision, right? Taken, not taken decision. We want to recycle ALU, right? To determine that decision, right? For that determination, you have to do subtraction, right? X1 minus X2. So ALU will do that operation, subtraction operation. So that means after execution stage, okay, this branch is taken or not taken, right? So then assume that this branch is taken. then what would happen? So execution stage, you know branch outcome. So based on that, you patch new instruction. So okay, so based on that decision, you patch new instruction. Okay, so we assume these two are equal. Okay, then what should happen? So you see the problem, right? So after branch instruction, you are supposed to execute subtraction instruction. But the problem is these two instructions are already inside the CPU. Look at this pipeline, right? At this point in time, addition instruction is in decoding stage, and patch unit is reading new instruction, which happens to be store word instruction, right? So these two instructions are already inside the CPU, right? CPU is about to execute these two instructions, which is wrong, right? You are not supposed to execute these two instructions. So what should happen? CPU should silently remove these two instructions. Okay, that is control hazard, right? So these two instructions are inside the CPU. So for correct execution, you have to remove these two instructions, right? These two by hardware. Okay, so that is the issue. Then that if you encounter this control hazard problem, we have some performance issue, right? We want to finish each instruction in one clock cycle. So assume that you have many instructions beforehand. Then at this clock cycle, a branch instruction is done. And next clock cycle, we want to finish next instruction. So every clock cycle, every one clock cycle, we want to finish one instruction. But because of this branch instruction, because of this control hazard, next instruction, subtraction, that is taking 1, 2, 3 clock cycles. 3 clock cycles for execution, right? Because you have to nullify, you have to remove, you have to flush out these two instructions. Okay, 3 instructions. Performance issue. Every clock cycle we want to finish one, but because of control hazard, next instruction, subtraction, is taking 3 clock cycles, right? So can you then somehow can you reduce these two bubbles to one so that we can reduce some performance penalty? So this one, Hongchan, can you please?
Reducing control hazard. To reduce two bubbles to one bubble, add hardware in ID stage to compare registers and generate branch condition, but it requires additional forwarding and hazard detection logic. Why?
Okay, thanks. Somehow we want to reduce these two bubbles into one. We want to remove this one bubble. Okay, for faster execution. So like this. Then probably you can resolve branch in decoding stage instead of execution stage. Okay, you want to move the branch resolution, these two branch resolution, two operations into decoding stage. But nothing is free, right? You have ALU in execution stage, but in decoding stage, you don't have ALU. Then how come you resolve? How come you compare these two registers? So nothing is free. So you have to add some hardware component. You need to add adder in decoding stage, comparator, or right. So if I draw hardware block diagram, decoding stage, you have register file reading two registers. That is decoding stage, right? And then taking these two, so they're supposed to be passed to execution stage, right? You have ALU, but to resolve branch in decoding stage, you add some hardware like adder or comparator. So you tap that line into here like this. So adder will do subtraction. Okay, or just comparator, simple comparator would be okay. Okay? So that will take care of that operation. Taken, not taken decision. So it is generating zero out. Right? So you use that signal to determine taken, not taken. So, and also how about this? Destination computation. That is easy, right? A program counter. Program counter is coming from PC register. So somewhere we have program counter register, PC register, DNQ, and this one output is PC. We call this program counter. So tap this line, right, to get this, and sign extension, right? Sign extension that is coming from instruction. So patch stage, right? You are reading instruction, and that is supplied to register file. You tap this line to get immediate, then go through sign extension logic, right? Then that is the one. This one is the one. So you add these two, right? So you need to place adder here, sign extension and PC. That will be branch destination. So decoding stage, you can do that branch resolution, right? So if you invest some hardware, nothing is free. So if you are able to resolve branch in decoding stage, then pipeline execution diagram looks like this. So based on that decision, taken not taken decision, you patch new instruction. Okay, then you need to take care of this one instruction which is not supposed to be executed, right? Patch unit read that instruction. So that instruction is inside the CPU. So you have to nullify, flush out, remove that instruction into no operation silently by hardware. Does it make sense? Flushing out, nullify, right? Changing that instruction into no operation, that is easy. We already know how to implement, how to design that mechanism in hardware, right? Remember load use case? This one, load use case. So here, right? You have to stop the pipeline for one clock cycle. Then if you look at this timeline, this particular clock cycle, you have a memory access stage and decoding stage, right? And patch stage will be below. And the question is, what is in execution stage? Right? Memory access stage, decoding stage, and patch stage. So in between these two, you have execution stage. And what instruction is in here? So you have to place no operation into execution stage. Otherwise, you are executing same instruction, 2 times. That is wrong, right? So we already know how to design, how to flush out, how to insert no operation, right? But the fifth milestone, if you open this, I'm asking you to resolve branch, conditional branch, and unconditional branch in execution stage. X stage, right? Execution stage. That means what? That means this pipeline, right? So you have to flush out these two instructions, not just one, right? So branch is resolved in execution stage in the class project. Okay. So based on that, you patch new instruction. So you have to remove these two, the instruction in decoding stage and the one you patch it, right? Does it make sense? Any question about this? Okay, let's talk about how to implement that mechanism, how to flush out. I already explained to you load use case, right? But let me open this one, pipeline number 2, next PowerPoint. So last time I showed you, right? So the load use case. So clock cycle number 3. What is clock cycle number 3? This one. Clock cycle number 3. Remember, you have load instruction in execution stage, end instruction in decoding stage, patch stage is reading new instruction, which is OR. And next clock cycle, what should happen, right? That is the one. So here, memory access stage, you have LW instruction. Try to draw, right? Patch, decoding, execution, memory access, write back. You draw that pipeline in your brain, in your head. Okay. So mem stage, right? Mem stage, you have LW instruction. And decoding stage, right? Decoding stage, you have AND instruction. Patch stage, you have OR. And what is in execution stage? Execution, right? So you see, visually, you can visualize that, pipeline in your brain, right? Then get some, good idea what you have to do, what should happen, right? So here, clock cycle number 3, that is the status. Next clock cycle, what should happen? LW instruction is moving, right? But these two got freezed, don't move, right? These two, you two don't move. Then what instruction is in execution stage? If you don't do anything, what is happening? Next instruction, this instruction, and the instruction is moving to copy to execution stage, right? Like this. So you have to play with that, pipeline register. So ID to execution, the pipeline register in between these two, right? This one. So you are supposed to pass no operation control signal to execution stage to make it no operation. Okay, so there is one, and this is the. And how about this branch control hazard issue? Okay, this one. Serin, are you there? 성주? 노성주? Come on. Come on. What is happening? 김서영?
When The branch condition is resolved. Other instructions are in the pipeline. It works like not taken prediction. If branch turns out to be taken flush instructions.
Okay, thanks. Okay, in this pipeline execution diagram, we are assuming branch is reserved in memory access stage, not execution stage. So there could be many different implementations, not many, several different implementations, depending on your design choice. How do you design, right? It is your design choice. Instead of resolving branch in execution, I want to resolve branch in memory access stage. Okay, so in this particular design, we assume branch is resolved in memory access stage. If you look at this slide, pipeline, slide number 15. Okay, look at this. Check out this control signal. Comparison. BQ, right? BQ, X3, X4, this label. So that comparison, subtraction, right? The comparison is done in this ALU. ALU will do subtraction, right? But if you look at this schematic diagram, look at this signal, branch, okay? Branch control signal is passed to execution, then passed to memory access stage. Then this AND gate is taking first input from this control unit and second input from ALU, right? Zero, this zero output. So by taking this, it can tell you, okay? So follow this line output. Output is connected to this multiplexer. This multiplexer is selecting what? PC plus 4, one input, first input. Second input is what? Second input, that is PC plus PC, right? PC. PC plus second input, sign extended immediate. So branch destination. Okay, branch destination is passed to execution mem stage. Then based on that control signal, AND gate output, that control signal, this MUX is selecting target PC plus 4 or branch destination. So in this particular implementation, okay, in this particular implementation, a branch is reserved in memory access stage. Okay, so based on that, you are reading new instruction. So that means you have to flush out. So these three, AND instruction or addition instruction, these three are in the pipeline inside the CPU. Okay, so you have to remove these three instructions from CPU. Remove means change those instructions into no operation by hardware. No operation. Okay. This one, I'll talk about that after explaining the design detail. Okay, branch prediction stuff. Okay, don't worry about this. Okay, if a branch turns out to be taken, this branch turns out to be taken, then you have to flush out these three instructions. Okay, these three instructions. Okay, so this one we already talked about that, right? To reduce two bubbles to one. Okay, two bubbles to one, you add some hardware in the decoding stage, right? So based on that, you can do this. So let's implement, let's physically design that mechanism. Okay, how to flush out that instruction, okay, inside the CPU. So this is the one schematic diagram. Okay, so in decoding stage, right, you have patch stage, pipeline register, decoding stage, pipeline register, execution stage, register, this one, register, and so on, right? So here, we have a comparator equal, right? This one is comparator, okay? Or, adder, subtractor, right? Adder, comparator. So that guy is comparing these two, okay? These two registers you read from register file. Okay, then check out this output. That is controlling if that output is 1, meaning these two are equal. Comparator is comparator, right? Comparator, compare. Comparator. How to design comparator? How to design comparator first? Any idea? Comparator? How to design comparator? Compare two registers. You can use exclusive OR gate, right? Instead of using adder, more cost-effective way of designing comparator is you can use XOR gate. How come? Right? Think about this exclusive OR gate. And the truth table, right? You have A and B. B and Y. 0, 0, 1, 1, 0, 1, 0, 1. So Y is what? 0, 1, 1, 0. Meaning what? These two are equal. These two are equal, AB, then 0. Right? So you can add what? You can add inverter here, right? To make it 1. Right? So inverter 1, 1, right? And then you have 32. 32, 32. That means you 32, 32, 32 XOR gate. Right? So simple, right? Comparator. Right? So comparator will receive 32 bit data, and you have XOR gate, right? 32 XOR gate, right? XOR gate. Then if I draw some detail, then what? Then inverter, okay? Inverter 32 inverter. Then final AND gate. Right? 32. It has 32 input. Right? Everything is 1, then output is 1. So that is comparator. Simple, right? Comparator, right? 0 output. 0 output. Right? Anyway, that is the one. This one, comparator. So again, this comparator will give you 1 if these two are equal. These two are equal. So 1 means what? 1 means you are selecting what is this? Okay, so you are selecting this one. That is branch destination. Okay, PC plus second input is PC, and first input sign extended immediate destination, right? So you are selecting this one. So that goes to program counter. So rising edge of the clock, PC will be updated, okay, to that destination. Then that control signal also controlling this pipeline register. Okay, so let me show you. This one is better probably, right? So comparator, this comparator is providing, and also this control signal. Control signal by doing AND operation. That guy is providing taken not taken decision essentially, right? Taken one, branch is taken one, right? One means you are selecting. Second, branch destination, right? And then you are also playing with that pipeline register, which is located between patch and decoding stage, right? Pipeline register. So when you pass, that means what? That means you want to pass no operation by using, right? By using this pipeline register, you want to pass no operation to decoding stage. Decoding stage, right? Pass. Next clock cycle, you want to pass no operation. Let me go back here. Next clock cycle, right? Next clock cycle number 2, clock cycle number 3. Next clock cycle, rising edge, right? You want to pass what? Here. Pipeline register between patch and decoding stage. You want to pass no operation, right? By playing with that pipeline register. Okay, patch, decode, in between, right? So, so one way to that that schematic. That schematic is showing this. What? This one is showing that is patch, decode, register, flip flop, right? And then it seems like it is using what? Enable or clear, right? It has clear input. This DNQ, flip clock, clear input. That is what? That is a reset. Actually, reset input, clear, right? Clear means you want to clear this output to 0. Okay, output to 0. If clear signal is asserted, clear at the rising edge, of the clock. Let me make it more realistic. Clock, right? If clear signal is asserted, clear is asserted for 1 clock cycle, typically 1 clock cycle. That clear? Then at the rising edge, of this clock, right? You want to clear this output to 0. 0 means what? 0 means, right? 0 means no operation, right? Machine code all 0 means, there is no operation, right? This is one way, but I do not recommend that implementation because it is okay functionally. So you are connecting this flush, taken signal to this reset input. The reason why I do not recommend that implementation is because reset input, this clear input in flip-flop, that is typically connected to a reset button on your computer. Reset button, you physically press the reset button, right, to initialize, to start start fresh, right? So I do not recommend that implementation. That reset is use that purpose, the actual physical reset purpose. So instead, another way to implement that flush operation. It's simple, right? You can use multiplexer. So patch to decode in between, right? You have instruction memory in patch stage, reading machine code, that is instruction in patch stage. So you place multiplexer right here. So either normal instruction or second input, which is all 0, 30, 0, which is no operation. Sorry, 32 or 32 zeros, the operation, right? Then adding multiplex, that is connected to this register. Adding multiplexer means you need control signal, right? Selection signal. So you can connect flush, that flush, flush, that flush, right? Comparator output, right? To that multiplexer. So if that flush, right? Flush is 1, then you are selecting this guy to this register. That means at the rising edge of the clock, this guy flip-flop is passing no operation, right, to decoding stage. So implementation, right, design is pretty simple. If you already have done false milestone, that design is super simple. It will take a few minutes actually if you think logically. Any question about this? So some animation. Okay. So assuming CPU is executing these instructions, and also we assume branch is taken, BQ, that is taken, right? So this is the status of the pipeline. Decoding stage, you have BQ, okay, and patch stage is reading and the instruction. Then what should happen next clock cycle? Okay, obviously we assume, right? We assume branch is resolved in decoding stage in this PowerPoint. Next clock cycle, BEQ is moving to execution stage, right? And the instruction is supposed to move to decoding stage, but the problem is branch is taken. So and the instruction is not supposed to be passed, right, to decoding. Instead, no operation should be passed. And then patch stage is reading LW instruction. So next clock cycle, this should happen. Okay, again, branch is taken. Okay, so that is controlling multiplexer. And here you are passing no operation. Okay, no operation to decoding stage. So next clock cycle, DEQ is moving to execution. And decoding stage, you are passing no operation, right? So no is in decoding stage. And then patch stage is reading instruction from the correct pass, L2, this label, this location, because branch is taken. Okay. Okay, that is about control hazard problem and how to resolve that that issue by hardware. Any question so far? Silence is not good sign. Silence, I'm very worrying. Silence is not good. Okay, so that is the one. Okay, and let's go back to pipeline number 1 slide and talk to you about branch prediction. Branch prediction. Okay, this one, 백민수. 설지원. Please. 영섭. 이영섭. 조재건. Okay, let me ask to mute. 한지상.
Longer pipelines can't really determine branch outcome early. Stall penalty becomes unacceptable since branch instructions are used so frequently in the solution. Branch prediction. Predict the branch outcome in hardware. Flush the instructions that shouldn't have been executed the pipeline if the prediction turns out to be wrong. Modern processors use sophisticated branch prediction. Our RISC-V implementation behaves like a branch not taken predict. Fetch the next instruction after branch. If the prediction turns out to be wrong, flush out the instruction fetched.
Okay, okay, thanks. In commercial processor like Intel x86 we use for notebook and desktop, and the ARM CPU, smartphone CPU. So in commercial, commercial processor, control hazard is super serious problem. So why? Because they implemented a longer, very deep pipeline. Okay, for example, Core to Duo has very old, right? 10 year, almost 10 years old. CPU from Intel has 14 stage pipeline. And probably you don't know about Pentium 4. Pentium 4 in 2000 around 3 or 2, around that time, right? 18 years ago, right? Pentium 4 processor. You know how deep the pipeline is? How many stages Pentium 4 processor has? 38 pipeline stages. 38 very super deep, right? So if I draw pipeline execution pipeline, it looks like this. Patch 1, patch 2, patch 3, and decode 1, decode 2, decode 3, and execution and 1, like this. 38 pipeline stages, right? And assume that in this pipeline, super deep pipeline, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7. Let's say 8, 9. Okay, 8, 9, 10. D4. Let me cook up. Okay, D5 like this, and assume that branch is resolved in E3, 11, 12. Assume that branch is resolved in E3 stage. Then Also assume that branch is taken. That what would happen? Branch is taken. Based on that decision, you fetch new instruction in clock cycle. Clock cycle number 13. Clock cycle number 13. You are reading new instruction. Patch 1, patch 1, patch 2, so on. Then control result, right? Then what should happen? All the instructions. How many instructions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 actually, right? 11 instructions in the pipeline, right? 11 instructions should be nullified. Big penalty, right? Super big penalty. And even more serious, that branch instruction. Let me use risk 5, just risk 5 instruction, because you know x3, x4 is label. That frequency of branch instruction, how often do you think CPU would execute that branch instruction? When CPU execute your real life application program, your sorting program, for example. So rough statistics is every 1 out of 5, 1 in 5, 1 in 5, meaning 20%. 20% of instructions are branch. That is rough statistics. Okay, so 1 in 5. So 1 in 5, you encounter this situation. So 20% of the time you have to flush out is 11 instructions if branch is taken. That is a serious problem, right? Super serious problem. So computer architect came up with this idea, branch prediction. The prediction, right? Prediction. So I don't want to wait. Prediction. So I don't want to wait until clock cycle number 12 to determine taken, not taken, not taken, result. Okay. So when I read branch instruction, I want to predict. Okay, that branch, I think that branch would be taken. Okay, that is done by hardware. So you have inside the CPU. Inside the CPU, you not only have those patch unit and decoding unit, execution and so on, but you have super big hardware that is called branch predictor. Branch predictor, very big hardware component. Okay, so when you read that branch instruction, that branch predictor say, okay, I think that branch outcome would be taken. So if that guy say, okay, branch would be taken, then next instruction, next patch 1. Patch 1 is coming from that destination, this label, not next instruction, not PC plus 4. The next instruction, not this one, but the one from that location. How come, right? How come this guy know branch outcome? It is based on history. So once you execute the program first time, your program first time, then this branch predictor is recording that output. Okay, I know from the previous execution that branch is taken. I know that it says, okay, the instruction location PC. Let's say this instruction is located at 100 branch instruction. Okay, program counter 100. Okay, and that from the previous execution, I know that branch is taken. Taken history, and I know the destination is this label L1. It is recording. This guy is recording that information. Okay. And next time you execute same program, you check out this hardware. Hardware will be referenced. Okay. So based on that program counter, read that information, and then this one is taken in the previous execution. So better to predict that to be taken, and I know taken, and that is L1. Destination is L1. So design is very complicated. Okay. So but every high performance commercial processor has branch predictor inside these days. Okay, because control hazard is super serious problem. So if you want to know detail about this branch prediction, probably you can join graduate school. Okay, that is a little bit advanced topic. So in graduate school, we talk in detail about this branch predictor. Okay. But our RISC-V implementation is working like branch not taken predictor. Why? Why? So if you think about pipeline execution diagram of our CPU, simple pipeline, 5-stage pipeline CPU, it looks like this, right? Branch, instruction, fetch, decoding, execution, mem, write back. So regardless of branch outcome, taken, not taken decision, our CPU is reading, always reading next instruction, PC plus 4 location, next location. So it behaves like not taken branch predictor. I don't care about this branch outcome. I'm going to read next instruction all the time. So not taken branch predictor. Okay, it looks like, right? And a branch turns out to be branch prediction turns out to be wrong. That means this branch is taken. Branch predictor turns out to be prediction turns out to be wrong. Then you have to flush out. Okay, flush out that instruction from the pipe. Does it make sense? Okay, that is the one. Okay, pipeline summary. This one, Hayomin, please. Okay, Johaemin.
Pipeline summary. Pipelining improves performance by increasing instruction throughput, executes multiple instructions in parallel. Pipelining is subject to hazards, structure hazard, data hazard, control hazard. ISA affects the complexity of the pipeline implementation.
Okay, so that is summary page of this PowerPoint. And second PowerPoint. So we need to talk about the last topic, one last one before closing out. Pipelining. So if you remember the single cycle CPU design, the last thing we did is performance evaluation. How fast, right? How fast CPU is able to run clock cycle, right? Maximum clock cycle. So we need to evaluate, right? That performance, the clock cycle issue. That is happening all the time in the industry, right? You design hardware, and then next thing is evaluate how good your hardware design is, right? How good your software is, right? After writing software, you have to evaluate, right? And how good your hardware is, you have to evaluate also, right? So clock cycle evaluation, right? Maximum clock cycle, maximum operating clock frequency, right? You have to evaluate that. So pipeline CPU is able to run at, for example, 3 gigahertz, 2 gigahertz. What is the maximum operating clock? 1 gigahertz. What is the maximum? Okay, or 3.2 gigahertz. Okay, so what is the maximum operating clock frequency? So how to measure this clock frequency? That is determined based on the critical path delay. Right? How long it takes from flip-flop to flip-flop. Right? Remember? So you have PC, pipeline register, program counter. Okay, then there is patch stage, right? And pipeline register, okay, and decoding stage, and then execution stage, and so on, right? So we have flip-flops, right? Flip-flops. So you have to measure, and then in between these two, you have some digital logic, which is combination logic. So combination logic, okay. So that is supplied and output like this. That is pipelining, right? So what you have to do is you have to evaluate the delay, right? That delay, this delay. And also from here to here, that delay, how long it takes, right? To propagate, for signal to propagate from here to here, okay? And same thing, from this point to that end point, how long it takes, okay? How long it takes. So delay pass number 1, delay pass number 2, number 3. So among these potential critical path, you need to select one, longest delay path. We call that critical path. For that, let me I want to draw some the path with PowerPoint. So let me change. Let me make it full screen, okay? And show you the path. Highlight about that. Setting, color. Okay, this one. Okay, so we have to evaluate 5 different delays, right? Patch stage delay, right? From PC, we have pipeline register, okay, to that pipeline register. This one, pipeline register. Also, we have pipeline register here, okay, and pipeline register, and pipeline register here. Okay, so we have to evaluate. Okay, better to use too thick. Discard. Okay. This one. Okay, we have pipeline register here, and this one, and here, this one, and this one. Okay, so we have to evaluate the delay of each pipeline stage, starting from instruction patch. So this is the one. This is the delay equation of the instruction patch stage. Right? So how come? So starting from PC program counter in patch stage, right? Sorry, this is not the one. Multiplexer, sorry, multiplexer. This is the one. Okay, let me remove. We have eraser. Oh, here eraser. Okay. Okay. Pointers. Okay. So from is program counter, right? Program counter to that pipeline register. So PTPCQ means the delay of that flip-flop. Okay, we have, that component, delay of flip-flop, right? Delay of that flip-flop, pipeline register, delay of that pipeline register, delay of this guy, and delay of this guy. That is a starting point, right? And then last one is setup time, setup time, setup time, setup time, setup time. Because you are going to take a picture, right? This guy, this flip-flop is going to take a picture. So before you take a picture, the object, right? Your friend supposed to stand still some time before, right? Before you press the button. So that is setup time. So equation is the flip-flop delay from here to here, right? Pen, and then pen, color, red. Okay. So delay, that delay. Okay. So this is the first one. Flip-flop delay, and then memory access delay, instruction memory, right? Memory access delay, then setup time. Okay, this flip-flop is going to take a picture. So before that, you need some, time to stabilize your data. Okay, don't move, right? Remember, don't move. Okay, I'm going to take a picture. And decoding stage equation. Decoding stage is a little bit complicated. Several paths. The first pass is this. First pass starting from that pipeline register, okay, and reading operand. That is the first pass. And second pass, because we placed that comparator here, you start from here and reading register, then going through this comparator, then that goes to, it ends here. Pro and counter. Flip-flop to flip-flop delay, right? This flip-flop to that flip-flop delay. Okay, so that is second pass you have to consider. And which pass do you think? Which pass is longer? Longer? Which pass is longer? 1 or 2? I think 2, right? Because you have to read both pass 1 and 2. You have to read from register file, right? And then first pass, you are passing that data to execution stage. But second pass, you have to go through this comparator and AND gate, then this multiplexer, then finally flip-flop. So second pass is taking longer time, right? Taking longer time. And that is the equation. This is the equation. You follow this equation. First one, flip-flop delay, right? That delay, that pipeline register delay, then register file read, okay, time, register file read time, then comparator delay, this comparator EQ, TEQ, and AND gate delay, right? This AND gate, and then you follow this pass, second pass, and then multiplexer delay, and then setup time, right? This flip-flop setup time, okay? And execution stage. Execution stage is simple, right? Starting from that pipeline register. So that is the one, right? And this is the one. Yes. Okay. So comparing these two, 1 and 2. Second operand, first operand and second operand. Okay, first operand, second operand. Probably second operand is second pass is taking longer, right? Because you have to go through 2 multiplexers, 1 here, but 1 and 2. Right? So that is the equation. TMUX, right? This one TMUX, 2 multiplexer delay, then ALU delay, ALU, then setup time, execution, right? Then mem stage. Mem stage is simple, right? Starting from that pipeline register. Okay, so the reading, right? That is one. Memory read, then setup time, right? Simple equation. And the last one is also simple. Starting from here, you are writing to register file, right? So mux delay here, mux, we have here mux multiplexer. Then register file setup time. Okay, register file is updated at the rising edge of the clock. So based on that, okay, let me change this slide. So based on these five, you have to select the longest one. Okay, so let's assume flip-flop delay is 30 picosecond. Okay, flip-flop delay to provide output to you, you have to wait 30 picosecond. Again, picosecond is what? 30 picosecond. 30 multiplied by 10 to the minus 12 second. I don't know how small it is. It's super simple, right? Can you feel that second? 10 to the minus 12 second. Okay. Multiplexer delay, 25 picosecond. ALU is taking 200 picosecond and so on. So if you plug these numbers into that equation, then you get these numbers. Patch stage, 30 picosecond delay, decoding this number, this one. So among these five, you have to select the largest number, right? So in this particular implementation, patch stage, so 300, these three paths are the longest. Same path, same delay, longest path, right? So clock frequency is determined based on these three: patch stage, and execution stage, and memory access stage, right? So that is okay. Hold on. Okay. So clock so the minimum amount of clock period, okay, clock TC, minimum, right? Minimum, min, Tmin. Clock period should be longer than that number. Tmin should be longer than 300 picosecond for our pipeline CPU to operate properly. Shorter, then we have problem. If Tmin is shorter, that means what? That means clock is running like this. Clock is faster like this. Okay, Tmin. Shorter, then we have problem. So pipeline register is not able to take a good picture, right? It is taking wrong picture, right? So, so minimum amount of time, right? Minimum should be longer. So maximum, right? Maximum clock frequency, F. F is what? F is 1 over F max. 1 over T min. 1 second, right? 1 second. Then how many how many this guy tmin you have in 1 clock 1 second. 1 second, how many you have? How many? Right? That is the equation. 1 second divided by tmin. That is frequency. How frequent that guy is? How frequent in 1 second? Right? How frequent? So if you do a simple math, 300 picosecond is equal to 0.3 nanosecond. Nano is what? 10 to the minus 9, right? Then that is 3.333 gigahertz, roughly. Okay, so our pipeline CPU is able to run that clock frequency. That is a maximum clock frequency, maximum. Okay. And one last thing is, if you compare single cycle CPU design, where is that? Okay, this one. Do you remember the clock frequency of single cycle CPU? So single cycle CPU, right? We evaluated the clock frequency of single cycle CPU, which is roughly 1 gigahertz versus here 3.3 gigahertz. So dramatic improvement, right? 3 times faster, right? But we are not satisfied with that number, right? It is actually, it is good, right? But not as good as we expected, right? What is our expectation? 5-stage pipeline, right? Then what? So potential speed up, right? Let's say the T, F, right? F max of single cycle CPU. Single cycle CPU, that is 1 gigahertz. Then the best performance you can achieve, pipeline, 5-stage, right? 5-stage pipeline, 5-stage, pipe 5. That is 5 gigahertz, 5-stage pipeline, right? But we have achieved what? 3.33 gigahertz. So good in a sense that it's much better than this number. But if you compare that number with this is not as good as we expected. So what is the problem? You remember Rondon example? Balanced pipeline, unbalanced pipeline. This is, what do you think? This is balanced or unbalanced? Unbalanced, because amount of time, okay, amount of time in each stage, compare the number. Different, right? 300, 290, 75, right? So numbers are different. It is not balanced, that same amount of time. So the design, we have some design issue, right? We want to balance the pipeline to get the best performance from the pipeline, right? So that is the one, one remaining issue, right? One digital design. That is a digital design issue, right? So which component you want to place in write back stage? Which component, which hardware component you want to place in memory access stage and so on. But in this implementation, patch stage and memory access stage, right? The majority of the time is 250, right? That is what? Memory access delay. That means you cannot do much with you cannot do much, right? Because the memory access delay is already 250, right? 250, right? So you cannot reduce that number anymore, right? So in this case, you cannot do, right? You cannot do much. So in computer system, the memory access delay is, memory access delay is super, taking very long, super long. So that is why we have special memory inside processor called cache. We want to somehow reduce that delay, the memory access delay. So that is achieved by cache memory inside the processor these days. So next topic will be the cache memory. So from Wednesday, we will talk about cache, the memory. This one is concluding our CPU discussion. We have spent a lot of time, roughly, more than 11 weeks, right? 12 weeks, I think. 12 weeks talking about this CPU, right? We started with discussing instructions, right? RISC-V instructions. Right? You practiced with programming, assembly. Then you know each instruction very well. Then after that, we move on. We switch it. We jump into CPU design. Right? How to design digital logic so that you execute, so that digital logic can execute the machine code. Right? We learned, and we did what? We studied two different microarchitectures. The first one, single cycle CPU. Second is pipeline CPU. Right? Pipelining is very good because you need to invest very small amount of hardware, flip-flops, right? Essentially, these flip-flops, right? Pipeline registers, right? And some the hazard detection and handling logic. So by adding that small amount of hardware, you can enhance the performance dramatically. So pipeline is very good, very intuitive, and very good technique to increase CPU performance. Okay, that is about for today. Any question? Before closing out? Okay, that is for today. And one last thing, we have what? We have Q&A session. Okay, Q&A session from 2 p.m. to this one, 2 p.m. to 8 p.m. Okay, so if you have some questions, then please come and ask questions to TA. I'm not sure I'm able to be there or not, but I'll try, but I cannot guarantee. Okay, that is it. See you on Wednesday. Bye. Thanks.